loaded to use. So I'm sure you guys have had a chance to look at the one up here on the board, and you probably noticed, what are all these little weird dotted lines there? So these are called leader lines because they're meant to lead your eye in terms of how and where components fit together. So it gives you a sense of both directionality as well as placement of components. So I just start off my discussion with a very basic demonstration of a sandwich. A sandwich, to do an exploded view, probably one of the most straightforward things is that it's in one axis. You have several distinct layers. Those layers are separated fairly far apart so that you can actually clearly see what each of these layers are. There is a clear delineation of the leader line so that your eye can actually see that everything basically stacks directly on top of each other in a straight line. So these are the things you want to make sure that you show in your exploded view, regardless of your device, is that you have a clear delineation of the components. You don't have too much overlap to where you're covering all the components, and also a clear sense of directionality with the parts. Okay, so that was the main idea behind this. So the next thing I wanted to show was, well, a lot of people have asked me, well, what if I have a tubular object? Does that same idea follow? And the answer is yes. So one of the things to think about when you're doing exploded views is just your angle of view, how you're looking at this particular object. So both in the case of the sandwich and this, whatever this is, I just made this device up, I have no idea what it is, but we're both looking down on the object, and that is very much a typical exploded view, angled view. But you can also draw your exploded views such that, especially with the vertical stack, you can actually go across the horizon line so that anything above it you start to see the underside of, and then anything below you start to see the top of. So this is helpful if you have detail that's both underneath and on top of components. So you can also draw it this way. I don't see students do this as much, but it's also a more descriptive view. So so far what I've shown is only in one direction, up and down, or up and down. But you can also do something much more complex, and that is something like this, where if you have a device that is has components that actually plug in different axes, you could end up actually needing to draw parts coming out in all these directions, up and down, out towards you and away from you in this direction, and same thing here in this direction. So the potential for multi-axial explosion is there. And so what I would encourage you to do is always think linearly in terms of the paths of your parts, if you can. Sometimes parts will have to do some funky stuff where it goes in straight, but it needs to actually go to the right and then fit in. But I would say try not to get into the weeds with this kind of complex movement, and try to break it down to just your major directions, axis of direction. Okay, so so if you're doing something like this, it's just a matter of and a simple way to do this, if you want, is to use tracing paper, and actually, if you can see a distinct parting line in your piece, is to literally trace over the first half. And I'm not saying that all of your objects are going to be as simple, but then you can just basically start to shift. I'm just drawing the lower half here, and maybe extrapolating the bottom shell. Now you're going to be able to actually observe and look at the components, but if you have maybe a photograph of the exploded of the object itself, you could actually print out the photograph and then just do trace paper overlays and actually explode it this way as well. So do you guys see what I'm doing? So it's just a matter of literally taking a static image of it and just pulling it apart. So what I was trying to show here is that you have side pieces So anytime you have something that moves outwards, you can use a combination of arrows and these little dots. So these leader lines, I've seen variations in long line, short line, long line, a dot, or little dashes. All right, but all of them are done fairly lightly. If you look at the one up on the board there, you'll see, I think it's just light dashes, but they're very helpful in showing the paths that where the parts go together. Okay, so anyway, that's something to think about. If you have screws, you'll notice that your leader lines actually are basically the center axis lines for these screws. And what's handy is when you have these types of lines, you can actually have it traced through several layers, so that if it goes through a hole in one layer, but then ends up in a boss in another layer, that center line actually helps to line up everything in the exploded tube. All right, does that make sense? Okay, so, yes.
So for the explosive view of that DC power jack,
Yeah.
like those two lines that going up, are they leader line or wire?
These are wires, actually. So what you'll find in some of your devices, and I don't know if any of you have something that complex with a PC board, but the wires typically I will draw still like attached to the PC boards. Sometimes you may have to lengthen them a little bit. Sometimes if you're drawing, if there are a lot of wires and they're very long, so the jack that you were mentioning, if it has wires that come off of it in the back, if they're very long, you can use the sort of this lightning strike idea to break the length a little bit, so that you don't have to draw all of that length of wire. Yeah.
So what I want to ask is, if I have an object that's attached to two different layers that gets explode, like how should I draw the leading lines? Do I just trace leading lines to two different layers?
So I'm not quite sure what you're asking.
So right now, like the DC power jack should be connecting to both the motherboard and the...
I just made this up, by the way, so I have no idea what this is, so, but yeah, it's a made-up device.
Okay.
Yeah, so, but what you're saying is, where it attaches here?
Let's say like the power jack has attachment to both the like the middle layer and the lower layer.
Okay.
Something like that. If
Yeah.
a part is attached to two different layers and they get explode, like should I draw leading lines to leader lines to both layers or just one of them?
With regard to the wire,
Yeah.
if it's attached to both, you don't really need leader lines. You can just show that it's attached to this and that it comes down and attaches to whatever's down here. Yeah. So that's why I said you might have to intentionally lengthen the wire just a little bit. Yeah. Anyway, I don't want to go into too much depth with this, because a lot of you have a very unique way for things to go together. But as long as you're using the leader lines to show parts and you're using the axial explosion method, you should be fairly clear in how things go together. Okay, and I can help you guys with it as you go along. Okay. All right. So that's somewhat of the basics of exploded views. By the way, if you do have a tubular object and you want to do it this way with a vanishing point, probably not a good idea, because you end up with a very big component in the front, but shrinking components at the back. So what I tell students to do if they like to do a horizontal layout is to use something that's more of an isometric method of drawing exploded objects. So you can see that the sides of these are all basically parallel to each other. So you guys see that? So it's a lot easier, and you can line it up with the center axis this way. All right? Okay. Okay, so let's talk about the next thing. As you do your teardown, I just wanted to alert you to some basic polymers, or plastics as they're better known, that you probably might run into. Now, it's not my aim to give you an in-depth plastics education, as there are a lot of different types of polymers. But generally, in the past, what I have seen when students have gotten to teardown, these are some very common things they encounter. First one is ABS. So this is a very common plastic because it is very impact resistant, and it doesn't shatter very easily. One of its hallmarks is that it is typically shiny. And if you've ever looked at plastic that's shiny, and if you tried to rub a groove in the surface with your fingernail and weren't able to leave a mark, typically that's ABS. So that's one of the ways you can kind of see if the fingernail test, I call it. So ABS is very common, especially for high impact applications. The next two that you'll probably run across are polypropylene and polyethylene. So you'll find these two in things like milk jugs, Tupperware, you know, syringes. The syringe bodies typically will be made out of this. So something like this probably would be one or the other. So sometimes you might want to look on your packaging for the products because they will actually tell you which one it's made out of. If not, I would look up these families and read what their properties are. When you do that, you'll probably be able to do an educated guess as to whether these fit within that family or not. So the reason why I'm bringing these names up is for you to be able to research a little bit more, to see, based on the properties that you're observing in the device, to see what they fit. Another one would be silicone. Silicone you'll see in medical products quite a bit because they're used typically as gaskets or places, objects that seal in things. So silicone is a fairly common material, and you'll also see when you look up silicone that it actually splits into a lot of different types of silicone and formulations. The other related material is thermoplastic elastomers, or TPE. You've heard that term. That is a family name for a whole giant family of elastomers. And elastomers, sometimes you'll find on medical products, they're squishy, they're kind of rubbery, but when you let go, they basically spring back to their original shape. Those are types of thermoplastic elastomers. What exact type they are, you will have to do a little bit more research into this particular family to see. So sometimes it can be confused with silicone because they're both kind of bendy, squishy. So it's something to kind of think about, maybe looking into both and seeing what works. And then lastly, you'll see acrylic. Acrylic is like plexiglass, clear, but it's somewhat brittle. It's not as strong as polypropylene or polyethylene in terms of being pliable, flexible, bendable without fatiguing and snapping. Acrylic is a little bit more brittle, but you still see some acrylic components, sometimes small ones, within the medical products as well. Okay. Lastly, in terms of plastics in general, there are two types. Ones that react and form well under heat. Typically, those are things like polystyrene, styrene. Marty talked about vacuum forming. Do you guys remember that? Mm-hmm. Typically, thermoplastics are used for that because you can heat them up, they get really, really soft. You can form them over a mold, add vacuum, and then you get this form that stays after it cures. It doesn't deform, it doesn't crumple up, it doesn't melt. However, thermoset plastics don't deal with heat very well. They basically deform badly. They don't really do what you want it to do. They don't just soften. And usually after that, you can't really do anything else with it after it's kind of melted and into a little bubble. So typically in manufacturing, you'll see a lot of thermoplastics used, a little bit more than thermoset plastics. All right, but each of these families up here have both of these types of plastics represented, though. Some are thermo, some are thermoset. So depends on the application. So as you can see, it's a very broad subject matter. I have to take a lot longer to talk about this, but these are some major ones that I've always seen show up. All right, so I just wanted to alert you to these, and I can leave this list up here if you want. So that's one thing. And then lastly, to help to measure and do some of your engineering analysis, you're probably aware that we've had these, but of course the biggest thing we have is the force gauge. Do you guys know we had a force gauge? So this is a force gauge. So if you need to, and it's out of power right now, but you can plug it into the wall, but you're able to do pushing forces on this. Ooh, wait, not that. It's still out of power. You can push down and it'll give you newtons or pounds, whatever you need, or you can put a hook attachment on this and literally set it up so that you can set up tests that test pulling forces as well. So, so this is a handy gauge that a lot of students use in initial engineering analysis. Now, how you actually get these forces and how you set up the pulling sometimes has to be fairly well thought out as to how you want to do that. But this is available for you. This is one of our older ones. We do have a new force gauge, which I don't know where it is right now, but once I see it, I will let you know. Now, these two are shore durometers. Now, if you need to measure just relative hardness of materials, these are units that these actually are numbers that are not associated with any known unit. They're really meant as a scale, a number scale. This is used in industry to basically make sure that produced parts are keeping to a certain hardness level. So the shore durometer rating is a way to do that. And the way you use this is basically this. So there's they're basically a fancy thumbtack attached to a spring that's attached to a scale here. Okay, so if you want to test hard objects like this metal right here, you can just basically press that needle part right against it, and you can basically see it's, I'd say, around maybe 70. So Shore D70 would give you a relative hardness of this particular metal here, probably steel. Now, if you were doing something basically, now make sure you get the right point, because this is a blunt point. So blunt short A's are meant to measure soft materials, so I can measure the shore durometer of my tensed up muscle here. It's about 30. Shore A 30. And if it's loose, I can also measure that too. It's about shore A 20. So you can see the higher the number, the higher the stiffness. So if you do want to characterize some of your materials in terms of hardness, then you can use those durometers as well, okay? So, but they don't really correlate to any particular known unit, but it is a standard. All right? We do have other, we have light meters, we have flow meters as well, where you blow into it and it gives you a reading as well. So if you need those, let us know. We do have a thermal camera, meaning it's like an infrared camera. You can point it at something, it can read the temperature. It'll actually show the yellow and green and red and all that. That's very sensitive. If you put your finger on there, it'll actually show the residual heat on the table as well. So some students have used it to get thermal readings off of things, so we have that as well. All right. So anyway, that's all I have, but do you guys have any questions so far? Okay. I will try to make my way around today, but like Christina said, you really should make sure that your engineering analysis is done, that your user observations are at a good place, and your user flow diagrams at a good place before you start to do a serious teardown. If you still don't feel comfortable fully tearing your stuff down today, that's okay. You don't have to do it during class, but at the very least, you need to start doing it later today or over the weekend to get your component matrix done and get your exploded view drawing started. So, all right? Okay, and like she said, Friday, be ready to get grilled on what you have and don't have on that checklist. So hopefully you guys have actually had a chance to read through that checklist. If not, I would suggest you do, because your rubric, your presentation rubric is basically based on that checklist, all right? Okay, all right.